IoT as a technology has become an essential need for many of the businesses. It has gone into a variety of range of applications such as automated home setups and are involved in everyday walk of life. There are many real world applications for Internet of Things, ranging from IoT enterprises to manufacturing to industrial applications. In our next topic, we'll take a look at MQTT, which is a very widely used protocol which is used in IoT devices. And with the number of increasing IoT devices, it has become a need in order to scale our applications which are using MQTT. For our next talk, we have three speakers: Nagarajan, who has more than 9 years of experience and has worked and led multiple projects solving scaling challenges of IoT. He is accompanied by Goushikaa and Sreekesh. Over to you guys.
Thank you, Sagar.
Yeah, thanks, Sagar, for the nice introduction. Yeah, hello all, welcome to the session on building scalable MQTT infra for multi-tenant IoT platform. Well, the topic might look a little longer or a little bigger in terms of the number of words, but it sets the agenda for the whole talk itself. So we'll talk about each and every word or every keyword in this topic, like what is MQTT, what is the platform that we are talking about, and what was the scalability challenge that we had, and how did we solve it. So before diving deeper into the session, let's introduce ourselves. Yeah, I'm Nagaraj. I'm working as a lead consultant at ThoughtWorks. Right now, working as a tech lead on one of the teams who is building this platform. Over to my colleagues to introduce themselves.
Yeah. Hi all, I'm Goushikaa. I'm senior consultant at ThoughtWorks with overall experience of 6 years.
Yeah, I'm Sreekesh, working in ThoughtWorks as a senior consultant with overall experience of around 8.5 years now. Okay, yeah. So let's quickly discuss this topic. So before going to the topic, let us set up the context of what the project is, all those things, and then we can discuss on the core part of the problem what we have solved it. So to share the initial requirements of the platform, right? Maybe we can take an use case. So suppose let's take an use case like if you are running an organization, and if we have many products in it. So let's say your product could be a manufacturing of phones, and next product could be a laptop manufacturing or devices like smart devices and etc. etc. In terms of IoT, it might be like sensors and other things, right? So each of these products, right? So when an organization is having this, they might be having an like a individual UI platform for them, UI service for them, and the services like device management, or for individual products, they will be having like license management, order management, those kind of stuffs. So as an organization, when there are wider range of products with them, right? So it's not an like good idea to solve the same problem like when we have a solution for one of it. So this is where the need of platform comes in. So when an organization have wider range of products with it, and in order to in order to avoid the duplication of solving the same problem, right? What we can have is in the platform, we can have some common services that are needed by each product, and which are termed here as the core services. And each product can make use of this core service for their needs. And in this case, we are talking about multiple devices like mobiles, laptops, and smart devices and other things. So in this case, we may need as a requirement of managing the device portfolios and monitoring the devices, all those things. So in this era, the data is the key thing for any business. And to take any business decisions, the data plays a key role. So the data that are produced as part of the device, which we call here as the telemetry data, So that needs to be collected and exposed for any analytical purpose for taking any business decisions. So once these platform setups are done, the intention behind this is to any product that comes in future, or even the existing product that needs to reach the market in faster time. So that is the intention behind the platform need. And as a platform, it needs to support millions of devices. And might be we can consider in case of IoT, there might be a lot of devices that maybe comes in. So we need the platform should support the load for millions of devices. And here we will stick with when we talk about the scalability problem of MQTT, we will talk about how we achieve 1 million load simulation and other steps. Yeah, so might be so this is the high level project context or the use case context which we have now. And the basic architecture for this platform would be like this. So all the services that are needed as part of this platform are containerized and running on top of the Kubernetes. So as a platform, each thing, there are core services which we termed, right? So the core services are this, like account management service, which will take care of user creation, then organization creation, like that. So the multi-tenant, the tenant here is the organization, which we are going to discuss. And other things like system service, which comes into picture for monitoring the health of each services. Then loggings, system loggings, as well as for any debugging needs, there are debugging service comes into the picture. So today we are going to discuss on MQTT that comes under the service of messaging service. So the messaging service here as a platform, it needs to support this messaging service for any communication among the services, or even to expose it in a public, right? So we need some sort of protocols and messaging support. So that is the service which we are talking about today. And for any services that we establish, it's need to have the security things like authentication and authorization in place. So that's where this permission service comes into the picture. And which is also a core service as part of the platform. So other next service is the database and storage service. So the need of this is as a platform, we need to provide a support to store any data, either in database or in the data like telemetry data inside the file system. So database and storage service helps us to store the data in any of the mode. So other services like device management service that are used for managing and monitoring the device portfolios, and to infer the or to view the current state of the device as part of the platform. And so when we talk about the data, right, telemetry data in the previous slide, we need to collect those telemetry data and store it in the storage services for the future analytical purpose. So that's where this telemetry service comes into picture, which plays a major role in collecting and processing the telemetry data from the device and storing it for analytical purpose. And next is the app service. So we have multiple devices that which we have discussed in terms of use case, right? So if we need to do any updates or roll out any updates or app installation, so app management service comes into the picture, where we can update the apps or packages as part of over-the-air updation. So all these services are exposed in terms of either by APIs or the protocols like MQTT, where the end users can consume it. So one of the end user is, or one of the end application might be UI portal, which will have the integration with this API. So where we can view any of the informations like device information, user information, and other stuffs. So likewise, we can also have integration with apps and services, which if there are any products, specific apps that need to be developed, which can leverage the existing core service feature, and the product team can take development of its own. And next is the analytical thing. So we have stored the data, but for any business decisions, we may need to run some analytics and or integration with BI tools to take any reports or the insights out of the data store. So that's where this analytics comes picture of the platform. And as well as the product integration of third-party services can also be integrated with as part of this platform. So there are two more things which you can see on the left side, that is security and observability. So whatever services or what are the things that are as part of the platform, the security is the main thing as part of as part of the development, starting from development. So security is the key thing here, and which will also be taken care by the platform. And for the individual service management and monitoring and things, observability comes into the picture. And I think we had a brief session before this where we talked about observability. So moving to next slide, all these core services which we talked are deployed on top of the AWS cloud platform, and the services are containerized with help of the Docker images and deployed on top of the Kubernetes services. And we also leveraged the Istio services that are mainly for the traffic management or to apply any custom policies and needs. So to configure the infrastructure need, we made use of Terraform scripts for provisioning the infrastructures. And we also had Jenkins as part of the CI/CD plugins for deploying continuous integration of the individual core services. Yeah. So today we are going to discuss mainly on this MQTT scalability problem as part of this platform. So before taking scalability issues and other things, I will give a short introduction about what MQTT is about. So MQTT is an lightweight PubSub protocol. We term the word lightweight here because it supports the messages with a small footprint code, because of the restrictions on the payload size limitations and fixed header of 2 bytes and other things. This protocol is specifically designed to support on low bandwidth devices, low bandwidth networks, and even with minimal CPU resource utilizations. So MQTT as a protocol, it has a high performance messaging system support. And when we talked about this PubSub protocol, right? So as a PubSub, it needs to have a publisher and subscriber. So when we take this diagram as a reference, so whenever there is a temperature changes or something like that, temperature sensor publishes a message to the broker. So here the temperature sensor who publishes the message is called as the publisher. And the broker here plays the role of accepting the messages and delegating the messages to the respective receivers who have subscribed for the topic. So I have called two things here. One is the subscriber and a topic. The subscribers are the computer and mobile device in this case, because it is trying to receive the message from the MQTT broker. And another term which we talked about is the topic. So the topic is the common contract between the publisher and the subscriber to have an agreement and to publish and subscribe the messages. With this short introduction of MQTT, let's move to what broker we have chosen as part of our product. So we used VernMQ broker as part in our platform. So the reason behind it is, so it supported the distributed and high performance things, as well as this VernMQ was built on with help of the Erlang language. So Erlang as a language, it has its own benefit of concurrency support and as well as the scalability things. So it supported both horizontal and vertical scalability, as well as the reliability of messaging, right? That was also good when we had a check on it. As well as the VernMQ broker supports basic authentication and rate limiting capabilities as part of it. So yeah, with this context, it's more like when we do these load simulation and other things, right? What are the things mainly needed? So observability comes here. So because if we are going to run any load or anything, we need to check like how the system behaves. So if you are trying to validate how the VernMQ is going to behave with a higher load, we need to integrate with observe some of the monitoring tools, right? And that's where this observability tools like Datadogs or Prometheus, Grafana all comes to like help us. And we specifically used Datadog for our platform needs. So in this case, when we integrate for the observability thing, right, with help of Datadog, we used a static configuration file for the VernMQ metrics readings. So whenever a VernMQ cluster or VernMQ node has been spinned up, we need to add an instance reference here as part of this configuration. So with help of this, we will be able to derive the metrics of the individual VernMQ missions. So observability helps us here to monitor the service health, as well as to get the metrics of the individual systems or the tools which we are using, as well as to read the logs or for debugging any issues. The observability tools comes into the picture. And some of the metrics that we really concentrated were on the CPU usage, memory usage, and container restarts. So based on these are some of the common metrics which are needed for all the services, because whenever a load is simulated or whenever a load is getting high from the end users, so based on the CPU usage or memory usage, we will be able to take in calls whether we to spin up or scale the resources or not. So that's where some of the common metrics these things comes into picture. And specifically on the VernMQ part, when we run load simulation, we have check up on cluster stability, as well as what is the number of open connections that are coming into VernMQ, and the processing, as part of the VernMQ broker, right? What are the number of processes that it is running as part of the system, and as well as the client activity. All these things are monitored as part of the observability, the Datadog integration. Over to you.
Thanks, Sreekesh, for setting the context. Yeah, now that we have the context on what this platform is about, our first goal here is to prove that our system can handle 1 million active devices to handle MQTT traffic. So in order to prove any system that it can handle such a load, we need to have a performance or load testing in place that will act as the proof that this system can handle such a load. So yeah, for us, we had to explore what are the different options available for us to use do the MQTT simulation. So at the start, we had checked the popular tools that are available. There are a lot of tools available, but we haven't went with the very popular ones like the Apache JMeter, Locust, K6, and Gatling. So we have did analysis on each of these tools to see whether that fits a need that we have to simulate 1 million MQTT connections. Yeah, so first one we started with is the Apache JMeter. So JMeter, it's there for a very long time. It has even might be the first top result when you do a performance testing as a search in Google, right? So it's there for a long time, and it is based on Java, and it is like a thread per user model. In our case, we had to simulate an MQTT connection per device. So in that case, then we have to model each and every device as a thread in JMeter. With thread being a costly operation in Java, a costly resource in Java, So definitely it required a lot of resources in terms of memory and CPU at the start. So we have used a bigger machines to set up the JMeter. And with the nature of MQTT being a long-lived connection, so it's a long-lived TCP connection. So it's not like HTTP where the connection gets closed on every request. Rather, here the channel between the device and the cloud will be stayed open as long as it can. So in the case of long-lived connections, to make sure that connection is long-lived, MQTT has to send heartbeats. And with the JMeter in place with the different rates, like we had like 1,000 different devices modeled in a single machine, but it was not able to keep all the connections alive due to the complexities or due to the constraint in the thread context switches. So we cannot, or we found that it required a lot of resources, and also it is not able to keep all the connections alive. So we have to set up a higher keep alive timeout, and then which is not an ideal value for us. So we had to move away from JMeter then. So next we landed upon Locust. Locust is a Python-based tool, Python-based load testing tool, which is an event-based tool. So they leverage something called as G events in the Python, and it has like since it's native on Python, it's very easy to customize. It's very flexible. We can do whatever that we can achieve with Python. We can do it with the Locust. And MQTT is not out of the box here, but it was very easy for us to implement our own version of client with MQTT, our own version of the simulated user as the with MQTT. It was easy to customize, but we landed up another bottleneck of cannot go beyond like 340 connections in a process. And that is because of the limitation with the MQTT client, the PAHO MQTT client that we have used, and which in turn was relying on the select system call. So Python by default has some static limit on how many system calls on the select can be open at any time. And it is not easy, it is not available to configure or update at the runtime. So only option is to rebuild the Python, updating the static variable in Python code, but it is not a easy option for us. And another option anyway is to like have more processes running for our need. But with our goal being 1 million, like 340, achieving 1 million with these many processes is not effective and efficient for us. So we have to look for other options. And then we quickly researched around the Grafana K6 tool, which is a Golang based load testing tool. And yeah, though its runtime is Go, all the customization, all these scenarios can be written in JavaScript. But the MQTT is not officially supported in the tool. So only the experimental or the POC version was available. Since we wanted more stable option, we decided to not go with this option. Yeah, and then we had the Gatling. So in our platform, the Gatling has been the go-to tool for us to load test or do the go-home testing for other services that Sreekesh has mentioned. So we have a lot of different services as part of the core platform, and this has been the widely used tool across the teams to test their services to match the SLAs. Unfortunately, the MQTT support is not part of the open source in Gatling. It is part of their commercial offering. But for most of our needs, the open source offering itself was enough. So then we found that it is easy to extend the open source version of Gatling to have the support for MQTT. So we decided to roll out our own implementation to support MQTT on Gatling. It worked at the end. Let me go back to this. Yeah, it worked though, and it is definitely faster than JMeter because Gatling has the actor model, which is a virtual thread model. So that it's definitely faster than the JMeter one. But when we tried with a more number of connections, like when we go beyond 15,000 or 20,000 connections in a single machine, and it started to see different failures in the connections. And since we rolled out our own implementation on Gatling framework, we had to deal with a lot of error handling and all, which is in a way a complex operation for us. And with the JMeter, I think the recent Java version, they also have this virtual threads available. But at the time when we are doing this exploration, it was not available. So we don't have any comments on that, on how it performs with the Java virtual thread service available right now. So now with all the popular tools, we haven't found enough support or enough capability in place to support our needs. We then looked around for different options. And then we found out in one open source GitHub project called MQTT Benchmark, which is a custom implementation in Golang. And Golang has the Go routines, which is again equivalent to virtual threads. And the runtime itself optimizes it to handle different Go routines. And we benchmarked it against that Gatling implementation, and we found that this MQTT benchmark is much and way faster and way scalable than that Gatling one that we had. So then, since it's just a custom implementation, we didn't have like enough support to configure and use it for our tweak it for our need. So then we forked that open source project, and then we customized it for our needs. Again, so it's not a full-featured customizable and scenario-driven tool like a Gatling or a K6, but we had enough configurations implemented so that we can tweak and play around with this tool. So this is our final tool. So we have rolled out our own Golang-based implementation, and another primary factor behind this tool is that we have the good skill set in the team on Golang. So it was very easy for us to roll out our own implementations whenever there is a need for customization. Yeah. Moving on. Now we have the tool selected. Then we have to decide on the setup. What should be our ideal setup on this 1 million load simulation or more than 1 million load simulation? So first point, the first question that came into the discussion was like, how many possible open connections that we can have from a single machine, right? So theoretically, at the first guess, we might think, okay, it is dependent on the resources. So as long as you have enough network bandwidth, enough memory and CPU available in the machine, you can have those many connections. Okay. So that's our initial guess. And then when we tried it on our own, so we found out, okay, there is another limit called open files limit. So for those who are not aware, like what is this open files limit? So for every connection that we create in Linux, for every socket, there will be a file descriptor created for that. And at the kernel level, there is a limitation on how many file descriptors can be opened in a machine at any time. So that is called as view limit. And I think by default, it may be like 65,000 in some of the machines, and some of the machines can be like 1,024, depending on that OS that comes in. And that limits that how many connections that you can have at any point in time. And it is easy to extend that. You can increase it to as many numbers that you want. So that was our first limitation we found. So we increased the open files limit. So in our machine, the default was, I think, around like 1,024, then we increased this to 100K. But even after increasing to 100K, we found that we are not able to go beyond like a 40K connections or 30K connections. And then we found out another problem is with the IP local port range. So for every connection that we create, it will be uniquely identified by a quadruple: source IP, source port, destination IP, destination port. So as long as you have this quadruple as a unique, you can have as many connections as your open file support. And given you don't go beyond the resources that is available in the machine. So in our case, the destination is static. The sources, the source ports will be different. So whenever you create a new connection, the source port will be dynamically picked up based on the available port in the machine. But the destination is a static destination. Like we have only one MQTT broker, the destination will be same. Since the destination is same, this open the IP local port range defines how many what is the port range that you can choose for creating new connections. So that way that's sets a limitation for your number of connections that you can create to a single destination. So yeah, moving on. we found that we can extend this. We can also like update this IP local port range. So we have updated it to support from 1024 to 65,536 as the range. So with that range, we can achieve like around 60K, to be exact 64K connections per source IP to destination IP. So in order for us to finalize simulation setup, there are a couple of options available for us. One is to have more interfaces assigned to the machine. Thereby, we'll have like different public IPs for those interfaces. And we can have like multiples of, like if we have like 4 interfaces for a public IPs, then we can have like around 250K connections from a single machine. That was one option. And another option, straightforward one, is to like spin up number of machines with each supporting 60K connections. So we went out with the easier one. So we had set up an automation script for us. So that will spin up like on demand, and each of the machine has the that Go MQTT benchmark bundled with it in the AMI. And so when the machine start up, it will start to simulate the 60K connections from that machine. And it all goes to the load balancer, and then that achieves the purpose for us. Yeah. So this is the setup that we had for our final load testing. So at the left side, you can see you have pool of EC2 machines, EC2 boxes that can simulate the load. We can increase the number of machines based on the load that you want to simulate. Again, that is automated. Yeah, the right side is the one that we have the infra. Sreekesh has covered it. So we have the EKS cluster, and inside EKS we have the 1MQ running in separate instances, and we all these things are behind network load balancer. So for such cases, we had to choose the AWS network load balancer. So choosing an elastic load balancer is not an ideal one for this sort of traffic where the TCP long-lived connections is expected. Yeah, I think yeah, this is with the simulation. Now over to Goushikaa on the scaling journey that we had.
Thank you, Naga and Sreekesh, for setting the context. So far we have seen the simulation part and the code that we have used for simulation. Next, we defined a process where our expectation was to define a resource that is required to support 1 million connections. For that, we wanted to define a process where we started with simulation. We will be monitoring the simulation run. Once the simulation run is done, we will validate whether our expectation is met or whether there is any issues. We will analyze it and try to update any configuration that are required to fix that issue. So this will be a cyclic process, and it will be a continuous one until we met that our expectation. So this is a process that we have defined for our scaling journey. So next comes the interesting part where we will be discussing on the failures that we have faced to identify our resources. And we will also discuss the possible solutions that we have identified for the issues. So as you can see in this journey, we have faced a lot of issues with different resources at different stages. We faced issues in 1MQ, Kubernetes, and AWS, and identifying those issues and solution for it was not an easy task. So we will be discussing each one in detail in the further slides. First, to start with, we have started with the single node setup, where we have a simple single 1MQ node, and we have a set of client machines which will be simulating the load. So as Naha mentioned, all this, so this 1MQ node is behind this load balancer. When the request is sent from the client machine, it will come to load balancer and then to 1MQ node. So our expectation was that when we simulate a node, that single node will be able to handle 200K connection. That was our expectation, and we were simulating load based on it. But we were not able to, or the single node was not able to process 200K connections. First limitation that we found was with the 1MQ, that is the process limit. 1MQ has a configuration where they are limiting the max number of connections that a node can process. The configuration is with process limit and max port. Initially, we configured it with 250K as a limit. So because of this, whatever simulation or how many runs we did, we end up seeing this kind of metric where a single node can process only 128K connections. When it reaches this 128K connection, it is not able to process the new connection, and also the existing connections are getting dropped. And the same can be depicted or seen in this metric. And also all these are happening when it reaches this 256K process. So for each connection, 1MQ creates two processes, that is system process and queue process. That's why we are seeing this 256K Erlang processes. So to avoid this, we increase this limit to 512K. So our expectation was it should handle more than 200K connection. And making this configuration change is not an easier one. We cannot simply update the environment variables. This is because of the limitation in 1MQ, where you need to update this configuration in a configuration file, build a new Docker image and deploy it. So we made this change, and we were expecting it to handle 200K connection. But still, it was able to handle only 128K connection. Next, after validating different logs in 1MQ EC2 instance, we came to know about another limitation with EC2 instance, where there is a filter. When it reaches this 128K connection, the connections are getting dropped. And this was visible when we looked at the EC2 instance logs. So there is a configuration, you can see it here, net filter connection track max. By default, it was configured to 131K connections. So what it does is that whenever we get a request, those connections are maintained in a table, contract table, and the maximum entry that table can have is 131K. And when it reaches that max, new connections are not getting accepted. So so to avoid this, we increase this contract max to 262K. And even after increasing it, we could see the single node 1MQ was able to handle only 180K connections. And now the limitation with net filter is also gone. And also with 1MQ, we have updated the configurations. Still, we are not able to achieve this 200K connections. And this is because of another configuration in Kubernetes, that is external traffic policy. By default, this traffic policy is configured with cluster policy. First, I will explain the flow of what happens when cluster policy is set. For example, we have two pods set up, and when a client sends a request to our service, first it comes to kubeproxy. Kubeproxy sends the request to the pod that is available. As per this diagram, kubeproxy sends a request to pod 2 that is running in node 2. So when the client sends request, the source is this 1.2.3.4. and the destination is this node 1. When kubeproxy forwards this request to pod 2, the source and destinations are getting changed. That is, the client ID is not getting preserved. Because of this, there is a limitation that already Naga discussed about port range limit, where each node will have only 64K port range. Because of this, we are seeing this limitation of node can handle around 180K connections. So now we have a question of why it is able to handle 180K connections with the limitation of 65K. Because when we were simulating the load, we have three nodes set up. So each node can handle around 65K. So as a total, it was able to handle 180K connections. So to handle more than 180K connection, we updated this traffic policy to local. Because of this, the client IP will be preserved. So when kubeproxy transfers that request to node 2, the source IP will not be changed to a node IP. Instead, the client IP will be used and forwarded to the node 2. After this change, you can see in the metric, the pod can process around 200K connections. So that is our expectation. Now we were able to handle it after making changes in different levels, that is in 1MQ, EC2 instance, and Kubernetes level. And we also wanted to try more. We wanted to know whether that single node setup was able to handle more than 200K connections. So to validate it, we were trying different load simulations, but we end up with handling only 200K connections. So we thought that is a limit that it can handle. But when we validated all the CPU and memory resources, in resource usage in the Datadog, it was within the limit. It was not using the full capacity. So we had a question of why we are not able to process more than 200K connections. And we done a lot of analysis done at different levels, but we were not able to find out. And with a surprise, we came to know about with the help of AWS support team, where there is a network level limitation in AWS per instance type. In our case, we were using M5X large. So with that instance type, it was able to support only 200K connections. And that is a limitation that is configured in AWS side. And there were no documentation of, there is a documentation of, there is a limitation at network level, but there is no limitation of that each instance can handle only up to this many connections. That was not there. So we were with the help of AWS support team, we were able to identify it. So why this is happening is that all the requests that is routed via this load balancer, gateway, and firewalls, all are automatically tracked by AWS. And whenever this limit is reached, the connections will be dropped. So that is an issue that we were facing. But if we are not using this load balancer, gateway, and firewall, but still we are facing this connection drop issue, it might be because of security group configuration. So if you are configuring any inbound or outbound rule, we can take this as an example where we have configured an inbound rule for 80 port. So here we are accepting all requests that is coming from any IP or any port. So as there is no limitation here, AWS will not track those connections and process all the requests that is coming to that instance. But if you're having or added any rule that is like 22 port, where we are configured to process only requests from a specific IP, if you have configured like this, then AWS will track all the connections, and when it reaches the maximum, it will drop the new connections. So this is a limitation with the AWS instance. And if you are using this ICMP protocol, whether you're configuring security group or you're using this load balancer or any automatically tracked connection configuration, this connections will be tracked and it will be dropped when it reaches the limit, only with respect to this ICMP protocol. So the one option is to, if you want to process more connection in a single node, then the one option is to increase the insert or move to the higher instance type. In our case, if you want to support more than 200K connections, then we should use M5X large or more configurations. So that is one option. And another option is to monitor these kind of issues. AWS provides this network performance metric. We were not aware of it when we were doing our simulation, but later we came to know about it. So where AWS provides this metric, we can monitor it. Whenever it reaches maximum, we can know what is the maximum limit for that instance, and we can use the newer instance type, or we can know about the limitation of that instance. So with this limitation and limitation in AWS, we set this limit of 200K connections for a single instance. And we were expecting whenever we increase more instance, it should handle, for example, if you are having two nodes set up, then it should handle 400K connection. That was our expectation. So to validate our assumption, we tried with multi-node setup, where we increased 2 more nodes, and our expectation was to it needs to handle 600K connection. So the setup is similar. We will have more client machines simulating the load, and there will be additional of 1 MQ nodes, that is 3 node setup. After adding this 3 node setup, we thought it will be able to handle 600K connections, but it was not the case. And the connections were getting dropped. So now we have found different issues at different level. Next comes the limitation with cross-zone load balancer. Because with the previous single node setup, the usage of network load balancer might not be there because there is only one instance. When we added more instances, it needs to route traffic to multiple instances, right? So in that case, we identify this limitation with cross-zone load balancer, where, as Naga mentioned, each connection should have a unique quadruple. So whenever, in our case, we can consider this as a client. So the client is sending 2 requests. So this is a client IP and port. 2 connections are getting simulated, and each request is sent to this EC2 instance, which is backed up by this network load balancer. So one request is sent to this network load balancer, availability zone 1, and the second request is sent to availability zone 2. So till now, until this load balancer, you can see the quadruple is unique. So we don't see any issue with it. But when the request is sent from network load balancer to EC2 instance, what happens is that in our case here, you can see both the connections are having same source IP and destination IP. Here the rule of unique quadruple is getting lost. Because of this, connections are getting resetted and disconnected. So why this is happening is that because of this client IP preservation. So this, we have made change in Kubernetes external traffic policy to use this client IP preservation. In our case, we wanted this client IP preservation, but because of this change, we were facing issue with cross-zone load balancer. Whenever these quadruples are same, a new connection is getting resetted. Because of this, we were not able to achieve the max connection that we were expecting. So to avoid this, one option is to disable cross-zone load balancer. But disabling it results in an impact of uneven distribution of load across multiple instances. As you can see in this metric, so one node is processing 100K connection and another node is processing 200K connection. So this is because of disabling this cross-zone load balancer. So for example, we can take, we have 2 availability zones and 5 instances. So in availability zone 1, we have 2 nodes, and in availability zone 2, we have 3 nodes. So when we get a request, that will not equally distribute. In the availability zone, since we have only 2 nodes, we have 15 requests to each node, whereas in availability zone, we have 3 nodes. It is getting distributed as 10. So because of this only, we are seeing a difference in load distribution and handling in different 1MQ instances. So to avoid this, one workaround that we thought is that to have equal number of instances in availability zone. In this case, if we add 3 nodes in each availability zone, it will be equally distributed and we might not see this difference of load distribution. So this is an issue that we have faced and disabled it, but with that we will have another limitation which we need to solve it by this workaround. Yeah. So after this, we were able to achieve or identify the resources that are required for 1 million connections, and we were able to configure it for our workload. Over to you, Sreekesh.
Thanks, Goushikaa. Yeah, so once these setups and other things are there, right? Still, it's not easy. Like though we, since we are exposing all these APIs and ports to the public needs, so as a platform we need to take some precautionary measures, because there might be some cases where a device may go on end-on retrying connections, or there might be some attackers who can try to simulate a number of loads to the same platform, right? So in order to safeguard our platform, we need to have some rate limiting capabilities that need to be set up. And likewise, so rate limiting comes into picture as for within within a specified duration, what is the number of connections that are allowed, or what is the messaging rate that we need to support. All those things we can take care as part of this rate limiting techniques. But still, like within a given point of time, what is the number of connections that a service can support, right? That we need to handle as part of the concurrency control mechanism. And so these could be the next steps, to support or to safeguard the platform from any distributed denial of service attacks. So with this, so these are the things that we need to consider when we are setting up a platform as well. So we have implemented this as part of the platform for safeguarding this attacks. Yeah, I think we reached the end of the slides and discussions. So yeah, time for questions.
Yes, folks, you can ask any questions right now, if you have any. I have one question for you guys. How much time did it took to reach from to like more than 600K connections? Like Goushikaa was explaining, going through like each of every stage. How much time did it took to like figure out everything?
So we were doing this analysis for a month or two, to identify all the issues.
So yeah, it included all the load setups and other things. But yeah, for every time, as Kaushik was mentioning, a new problems are rising, right?
Correct. Cause file descriptors, first you fixed it on every level of the request, right? Right from the load balancers to network to actual, in the platform, which is application, then in the kernel, in the operating system, file system, so on. So like there wasn't problem at every stage of a request which is being catered.
Yeah.
Yeah, it was a good learning experience for us as well. Yeah.
Do we have any more questions, folks? Come on, I need a quick emoji reaction from everyone. Just checking if you're not asleep. Yes, yes, people are there. Okay, I think we can move on to next talk.